be recording this. And then the second topic of the course is power series. And then the third topic of the course is multivariable calculus. Although really there we just mean we're going to do like differentiation. We're not actually going to get into like surface integrals and that kind of stuff. Okay. So that's how you would divide this semester into 3 parts. As of last lecture, we are done with the metric space part. Okay, so now we're in to the power series parts. And this is going to take us about 3 weeks. Really, it's only 3 weeks because we've got a quiz in there and then we've got a recharge day in there. But anyway, it'll take until 3 weeks from today will be our last lecture on power series, or at least that's how it's scheduled. Okay, so we're going to get started. Are there any questions before we start power series? No? Okay. Well, we've spent, half the semester in a very general context. For the power series section, we're going to specialize now. We're really only thinking about functions from the reals to the reals. So it's the same setting as last semester. We are always thinking about the standard metric. Okay. So things like compactness and uniform continuity, these concepts from the first half of the course will come up here, but we're always going to be in this one metric space. Okay, so the different metric spaces aren't going to come up here. So, in terms of an introduction to power series, I know you've all seen some of this in Calc 2. Or at least I hope you've all seen this in Calc 2. I hope they still teach it in that course. It's been, it's been a decade since I taught that. I want to start maybe kind of with something you did probably at the end of considering power series in Calc 2. Okay, so here is my question. Suppose you don't have a calculator. And you're just you're stuck on an island. Or imagine you're an ancient Greek. How would you compute sine of 1/2? How would you approximate that? Any suggestions? Okay, yeah, that's a good engineering answer, I'd say. What's the approximation you're using there?
First, 0th order Taylor series.
First, I think, but yeah.
Fair enough.
Yep. I mean, so one obvious answer would be just a polynomial approximation. Okay. Another answer would be, if you have a protractor around, you can actually maybe draw the angle and measure the sides and approximate the value of sine that way. Okay. But let's try a polynomial approximation. Okay, so we want what we want to do is find some coefficients so that, let's do, what do we want to do? Let's do degree 3. So I'm going to try to get a degree 3 polynomial and I want it to approximate sine of x. Okay. Any questions or suggestions?
I guess a suggestion for like finding the coefficients. I guess at this point, do we have derivatives?
Yes. Okay, so
Okay.
I should say this. Because we're focusing on functions from the reals to the reals, we have everything we learned last semester now.
Okay.
So we have derivatives and we have integrals.
Okay.
We also have like mean value theorem and that kind of stuff.
Okay.
I think the first thing we should do is make sure it matches it on 0.
Yes. Probably should, but I should probably make the question clearer first. Right? Because I didn't even say where we should approximate sine. Right? So let's approximate it near x equals 0. Okay. Now, we kind of opened up with, you know where we're going, so you're trying to suggest we do the Taylor polynomial, I think. Let me just point out before we jump into that, that's only one answer here, right? We could also do, like a least squares method to find some coefficients. Right? There's a lot of ways to find these 4 coefficients that will give us a good approximation of sine. Taylor polynomials are just one way. Okay. If you take a numerical analysis course, you'll find you'll get a lot of other ways that you could do it. Okay. But here's one idea: is that we'll try and match derivatives. Okay, so the 0th derivative, yes, and Brandon points out, yeah, we could do Lagrange interpolating polynomials. There's lots of different approximations we can do, but we're gonna go into the Taylor polynomials. 0th derivative is just the function itself. So the the polynomial at 0 would just be C0. If we want that to be sine of 0, the sine of 0 is 0. So we want C0 to be 0. Okay, now we take a derivative. Okay. Okay, and then we plug in 0. We see our derivative is C1. Our derivative at 0 is C1. We want that to be the derivative of sine at 0. The derivative of sine is cosine. And cosine at 0 is 1. So we want C1 to be 1. Okay? Now let's take a second derivative. 2c2 plus 6c3 x. We plug in 0. We get 2c2 We want this to be the same as the second derivative of sine at 0. Second derivative of sine is minus sine. That's 0. So we want C2 to be 0. And we're almost there. Take 3 derivatives, and we get 6C3. At 0, that's still 6C3. We want this to be equal to the third derivative of sine at 0, and that's a minus cosine. That's minus 1. And we solve for C3, and it should be minus 1/6. Okay, so we put this all together, and our approximation is P is x minus 1/6 x cubed. Okay. Everybody clear on what we did to approximate sine here?
I have a question about the motivation of saying let's take derivatives to be the same.
Uh-huh.
I can't remember. Do we have a theorem from last semester that says if two functions agree on derivatives that they're the same by some factor or something like that?
Well, we're going to have a theorem by the end of today.
Okay.
Okay. No, I mean, I guess, so this is one of the points I tried to make earlier is sort of, this is only one way we would approximate sine, and a priori, you know, it might not be the best way. And we're never gonna say it's the best way. It depends on what you're trying to do it for. But, you know, matching derivatives is something, right? So maybe that'll work, I guess, is kind of how I would motivate this. Is that okay?
Okay. Yeah.
Okay, now if we think about sine, there's a sort of graph of sine. If we stopped after just the first derivative, we'd have that approximation. Okay. After we get to the third derivative, where we're doing this minus 1/6 x cubed, now you see actually our highest order term is now negative. So in the long run, we're going to be a negative function. In fact, over here, you can see that we're just going to go down to infinity over there. And over on the left, we'll do the same thing, but in reverse. Okay. Is this a good approximation of sine? Well, it's clearly not a good approximation, you know, very far to the right or very far to the left. Whether it's a good approximation near 0 remains to be seen. Okay? But again, certainly, you know, we're not trying to claim it's a good approximation on the entire real line, and we know we can't even do that because sine is bounded and polynomials just aren't. Okay. So of course, everyone remembers this is the Taylor polynomial for sine centered at 0 of degree 3. So just to remind you of the formal definition of these polynomials, we'll define them. And we need to have a little hypothesis, is that our function needs to have that many derivatives. So suppose f of x has n derivatives at the point x equals a. Then we define the Taylor polynomial of degree n for f of x centered at a. Okay. It's the unique polynomial. I will denote a capital T sub n of x that satisfies that it matches all the derivatives up to the nth. So it should have T at a, it should be f of a, then its derivative should match. And up to the nth derivative. Okay. Questions so far? Okay. Now, if you go back to our example, you can see when we can find one of these just by putting in the coefficients, taking derivatives and solving for them. But what's going to happen there's a pattern that's always going to happen in that by the time, for instance, if you look at C3 here, by the time we solved for it, that's where we solved for it, and over here we had the third derivative of sine. By the time we solve for the nth, or maybe I should say the kth coefficient, it's going to be multiplied by a k factorial. Okay, because we're going to take these repeated derivatives. And we don't end up solving for a coefficient until it's the coefficient of, the constant term of the polynomial. That's what I mean. Okay. So we have a really easy formula. Well, depends on the definition of easy. I think this is a nice formula. The Taylor polynomial of degree n for f of x centered at a. You just do what we did in the example, you compute it, you find that it's actually the sum of each coefficient will end up being the kth derivative of your function that you're trying to approximate at the point A where you're trying to center this, divided by k factorial, times x minus a to the k. Okay, let me just note that when we have the zeroth derivative here, we just mean the function itself. And 0 factorial is just 1.
Is there any situation where 0 factorial is not defined to be 1?
No. 0 factorial is absolutely always 1. This is, and I would argue this is not even a definition. Here. What is k factorial? K factorial is the product from I equals 1 to k of I, right? Well, if you plug in 0 for k there, you get the empty product. And the empty product is 1. I guess that's a definition. Okay. So I'm just, when I say this, that's not me making a special definition of 0 factorial. That's me just reminding you that 0 factorial really is 1. And it should never be anything else. Okay, any questions? We go back to this plot. Kind of the question that the questions that we're interested in now are kind of where will this polynomial be a good approximation to sine? And how can we get a bound on the amount of error in this approximation? Okay, so sine here was the blue curve. The approximation was the green curve. Can we bound the difference between the blue curve and the green curve? Okay. So again, we got this formula. It comes straight out of just saying the derivatives should be equal. We want to look at error. So what we define is the remainder term. We call it a capital R sub n. That would be the function minus the Taylor polynomial. Okay. Again, let's just go back to our example. We look here, we're taking the function that's in blue minus the remainder that's in green. We're looking at the difference. So what are we seeing? Over to the right, in this particular example, over to the right of 0, the remainder is positive. Over to the left, the remainder is negative. Near 0, the remainder is very small. Okay, so if we plotted that, it would roughly look like, it would be R3 of x, 4 sine of x, centered at 0. And it would roughly look like at 0, it's 0. and then it increases very slowly up until it does something like that. And the same over here, although it's slightly negative, and then like that. Okay. Are you with me so far? Our goal is to show that this remainder term, which is the error, is small, although again, we can't hope that it's small on the entire real line. We can only hope that it's small when x is near a. Now, we are going to prove what's called the remainder theorem, which will give us bounds on this. You might remember that from calculus. In the proof, we're going to need Rolle's theorem. And I would hope some of you might remember this from last semester. Do I have any volunteers?
Is this the one where you have the function equal at 2 points at some point in between its function's continuous and differentiable, that its derivative is 0 at one of those points?
Yeah, exactly. So differentiable implies continuous. So we don't need to say continuous, we just need differentiable. If the function has two values, where f of a equals f of b, those have to be different values. Oops. That would be quite funny if I wrote that. Anyway, this has to be different points. Oh, and I don't want that to be a B, I want that to be a C. If f of a equals f of c, for some a not equal to c, then there is some point B between a and c at which the derivative is 0.
Is the between strict?
Yes. Yes. Yes, it is. So we can say that B is in the open interval between A and C. Okay. Now, how did I know that the between was strict? Let's think through the proof of Rolle's theorem. Anyone remember? It's a very short proof given other theorems we know.
We use the mean value theorem, I think.
Actually, it's the reverse. We used Rolle's theorem to prove the mean value theorem. You're right. It's this, Rolle's theorem is a special case of mean value theorem, but we actually used it to prove mean value theorem. So how did we prove Rolle's theorem?
Intermediate value theorem? For f prime of A and f prime of C?
So the problem is we don't know anything about f prime of A and f prime of C. It could both be positive or both be negative. And let me, I should probably be more careful there. I want f to be differentiable on the closed interval from A to C. I'll just give Maddie has it. It's the extreme value theorem. Okay, so here's, I'll just run through the proof real quickly. If what do we want to do? If if f of s is constant on this interval, then done. Okay, if it's constant on the interval, its derivative is 0 everywhere. Otherwise, it has a min or a max. By the extreme value theorem. Okay, and that min or max is a relative minimum or relative maximum, and we're using the result that the derivative at a relative maximum or minimum is 0. Okay? Put quotes around that proof. It's just a brief hint, a brief reminder about the proof. Okay, so like I said, Rolle's theorem is going to be a tool in how we're going to approximate the remainders. And let's get to that result. So this is the remainder theorem. There are many variants of the remainder theorem. I'm going to state here what's called the Lagrange form. So, well, Taylor series have the standard kind of sad story that during Taylor's entire life nobody ever noticed them, and then it was Lagrange who came along after Taylor and realized how important Taylor series were, and he developed all the theory, and it's him who I believe first proved the remainder theorem, and this will be his form that he stated it in. Okay, let's suppose that f is n plus 1 times differentiable it'll be easiest if we don't try and clarify, where it's different, where it's n plus 1 times differentiable on the closed interval of interest here. Okay. And let Rn be this difference between f and its Taylor polynomial, where let's actually say Tn is the nth, that's the Taylor polynomial of degree n for f of x centered at x equals a. Okay? Then, for every x, the remainder is, the remainder is by definition f of x minus Tn of x, but the remainder is also given by that. And I need to say that this is for some point B strictly between A and X. Okay. So what really should go here, if we want to quantify where we're differentiable, this would be between A and X. Okay. Now this B, the B depends on X. So for every value of X, obviously, we'll get a different value of B. Okay? Any questions on this before we prove it?
So we're saying that there's just this some point between who's, you know, the n plus 1 term is our bound?
Yes. And therefore, if you can bound this, if you can bound the n plus first derivative of f, then you'll get a bound on the error in the Taylor approximation. Okay, and the bound will be in terms of how far away you are from the center, and then you're dividing by this factorial, which is, it's really good that you're dividing by a factorial because factorials grow super quickly.
And we don't have that this n plus 1 is bounded because we don't know that it's continuous.
Well, we certainly, we don't know that we don't know that the n plus first derivative is continuous. Yes, that's correct. We don't know that. Okay. Because all we're assuming is that that n plus first derivative exists. Because we said we're n plus 1 times differentiable. Okay? Let me just restate this. What we really want I want, instead of an X, I want a C there. And let me just suppose, it doesn't hurt. I'm going to suppose C is bigger than A. That just lets me write the open interval A to C. Okay? So, think about the point A, that's our center, that's fixed. Think about the point C, that's where we care about the error as fixed. We want to find this point B. Well, we don't so much want to find it as prove it exists, okay? So, we're going to choose a capital K so that the function evaluated at C is its Taylor approximation evaluated at C plus this constant K times C minus A to the n plus 1. Okay, I'll admit that step, not very motivated. Okay, can we do that? I mean, yes, obviously, we compute f of C, we compute its Taylor approximation at C, and we can just solve for a K. So we can make that happen by choosing a K. Okay, and then we define this function, capital F of X, that's not an integral, that's just this thing. Will be this difference. Okay. So in here, that is the remainder. Minus here, this is something like we want the remainder to look like. Okay, except we've chosen this K to make it work. So we have the first n derivatives of capital F of X at x equals a are all 0. Okay. Why is that true? Well, if you take a derivative of f of x, you plug in a. Take a derivative of Tn of x, you plug in a, you get the same thing. Because that's how we chose the coefficients of the Taylor polynomial. And then this guy with the k, the capital K, well, you take the first n derivatives of it, and you plug in a, and you get 0. Okay, because all its derivatives are some number times x minus a to some power 1 or greater. Okay? So now we're just going to we're going to use Rolle's theorem. We just get to hunt for the roots here. The hunt for the roots of the derivatives. Okay? So We know f of a is 0. That's a special case of what we just wrote. And we know f of c is 0. Okay. Why do we know f of c is 0? It's because that's how we chose k. We chose k to make that true. Okay? So there is some point by Rolle's theorem, I will call it B1, that is between A and C, that makes f prime be equal to 0. Okay. So here's A, here's C, there's B1. Okay. Now, I hope you see what's coming. We got B1 because capital F of A was equal to capital F of C. Now you look at the derivatives. Well, we just found that the derivative at B1 is 0. But we also know that the derivative at A is 0. Why? Because the first n derivatives of capital F evaluated at A are 0. So now we're going to use Rolle's theorem. We're going to get a B2 in there, at which its second derivative is 0. So if we assume, assuming that, let's see, assuming we have a bk that makes the kth derivative 0, we find a bk plus 1 between a and bk that makes the k plus first derivative 0. We keep doing this until we find bn plus 1. So we know that the n plus first derivative of b, of f at bn plus 1 is 0. Okay, but on the other hand, we know the n plus first derivative of x, okay, is the n plus first derivative of f. I'm going to scroll back up to our definition of capital F. Okay, we take an n plus first derivative of that, we'll get the n plus first derivative of f. The Taylor polynomial does not have an n plus first derivative. I mean, it's 0 because it's a polynomial of degree n. And then you can see the n plus first derivative here will be this capital K times n plus 1 factorial times x minus a. Okay, let's see if I got this right. Oh, times, right. The x minus a goes away. Yes. And I realize I am out of time. If you'll give me another minute or two, I can finish this. So on the other hand, this is true. So capital K, what is it? We just solved for it. Okay. And you take that capital K that we just solved for. What is that? That's the n plus first derivative of f at some point between a and c, divided by n plus 1 factorial. Okay, go plug that back in to here. And you've got your theorem. The remainder, which is f minus Tn, is K was this, K is this n plus first derivative of f at a point between a and c, divided by an n plus 1 factorial. And then this says, I guess I should be looking down here, and then this is times c minus a to the n plus 1. There you go. Okay, so that was our reminder about Taylor polynomials, and just wanted to remind you that there is this theorem, the remainder theorem, that lets us approximate, or lets us say how good an approximation the Taylor polynomials are. And there's not much to the proof, you know, and I should also say, you know, all of this stuff that we're doing about power series, we could have done it last semester. Okay, it doesn't really depend on what we've done in the beginning of this semester. Okay, so let me stop there.